Family wants to create a fenced pen for their pet rabbits. La 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 la. So they're building a rabbit pen. This is going to be fencing along this side. This is length W. We have this side down at the bottom, which is also also W units long. And then we have L along the side of the pen. This side you get for free because there's already a house here. You have as much wall there as you want and it doesn't cost you any material. And they want us to cover the maximum area for this enclosure. So, what's the area of that enclosure? It's a rectangle, so its measurements are length times width. Fine. But this has two variables in it, which is not fine. We'd rather get this down to one if at all possible. So is there any way that these variables are connected? Any way we could get rid of L or get rid of W? Yes, there is. They said we have 24 meters of material to work with. So these three sides of the enclosure, meaning an L and two W's, must add up to 24 meters. Well, if that's true, then the length has got to be something like 24 minus 2W. We can use that. Any place that this expression contains L, we can put this instead. So our new improved area over here is L times W. And for L, I'm saying 24 minus 2W. That's an improvement because this only has one variable in it. And it would be improved even more if I expand it. W times minus 2W is minus 2W squared. W times 24 is 24W. And there we go. I did this in a funny order here because I wanted these to be in descending order. I'm a big fan of that, so I put the highest power of W first. That's all. So, we want this area to be maximized. What happens with problems like this is if you have a very tiny W, if your W value is extremely small, you get a skinny little pen with hardly any area. And then as you increase W, the area gets better. But if W gets way too big, you get a skinny pen the other way. You get a pen that's got ultra long sides like this and hardly any length. And that has hardly any area either. So the area rises for a while, but then it ends up dropping. And somewhere in the middle, there has to be a sweet spot right here where we get maximum area. And that is the point we're trying to find. What's special about this point, mathematically, is that the slope is 0 there. If you're standing on top of a hill, just in that one little spot, the ground is flat. So it has a slope of 0, which means its derivative is 0, and hey, we can get a derivative for this. So our general procedure is differentiate, see where the derivative is 0, and that point is going to be either the top of a hill or the bottom of a valley. Let's see if we can find it here. dA dW is 2 times minus 2 is minus 4, W to the 1, plus 1 times 24, W to the 0. There, that's our derivative. And it equals 0. That would mean 4W is 24, which would mean W is 6. Okay, so we're looking to build an enclosure with a width of 6. What's its length? Well, happily, we've got an expression over here that's all set up for finding the length. The length is 24 minus 2W, so it's 24 minus 2 times 6. Our length should be 12. So we want a pen that's 6 wide and 12 long. Now, that isn't quite what they asked for. They often do ask what are the measurements which would give the maximum area, but for this one they actually say what is the maximum area. They don't care how we get it, they're just saying what's the biggest, what area are we going to get for this largest possible pen? Well, the area is length times width, which means it's 12 times 6, which means the maximum area, A max, is 72 square meters.